This video details our project work Phase 1, Review 2, on Explainable AI for heart attack prediction through retinal vascular biomarkers. The agenda includes the introduction, statement of the problem, scope, methodology, design, implementation, results, test cases, conclusions, future work, and references. Our project predicts heart attack risk using retinal images and vessel-based biomarkers like CRE, CRVE, and AVR. We use a machine learning model for classification and an Explainable AI, or SHAP, module for transparent, medically interpretable predictions. Current diagnostic methods are often costly or invasive. We aim to develop an automated, non-invasive, and explainable system using retinal vascular patterns and SHAP to detect early cardiovascular risk and aid clinical decision-making. The scope involves developing a machine learning system to predict heart attack risk from retinal fundus images. We extract various vascular biomarkers, improve early diagnosis, and integrate SHAP for transparent results. The target audience includes patients, clinicians, and healthcare institutions. Deliverables are a trained ML model, a complete biomarker extraction pipeline, SHAP explainability reports, and comprehensive documentation. Inclusions cover image collection, pre-processing, feature extraction of retinal biomarkers, ML system development, and SHAP integration. Exclusions include the diagnosis of all heart diseases, real-time scanning hardware, full clinical evaluation, or EMR system integration. Our methodology involves collecting and pre-processing retinal images, performing vessel segmentation, and extracting biomarkers. We then train and evaluate a random forest or XGBoost model, apply SHAP explainability, and deploy a web interface for risk screening. The architecture involves data flow from the retinal dataset through pre-processing, vessel segmentation, and biomarker extraction. Data is then split for ML model training, risk prediction, and SHAP analysis before generating a final report for the user or clinician. The use case diagram illustrates interactions where users and clinicians can upload a retinal image and view prediction results. The admin can also manage the dataset. The class diagram shows key components: user, retinal image, vessel mask, biomarker extractor, prediction model, and explainable AI, defining their attributes and relationships. This sequence diagram shows the flow when a user uploads an image. The system pre-processes it. The biomarker extractor computes features, the model predicts, and SHAP returns the explained result. We use algorithms for image pre-processing, UNet or morphological filtering for vessel segmentation, skeletonization, and morphological feature extraction. Biomarker extraction computes key features, while random forest predicts risk, and SHAP provides interpretability. The required hardware environment includes a minimum of a Pentium dual-core or i3 processor, 120 GB hard disk, and 4 GB RAM. The software environment is based on Windows or Linux, using the Python language. Implementation uses Python with libraries like OpenCV and PyTorch. The process involves uploading the YOLOV 7 model and dataset, training the model, and then using it to detect and categorize objects in images, displaying bounding boxes and class names. Key code segments cover image and mask loading, importing necessary libraries like CV2, NumPy, and SHAP. A function is defined to safely load the fundus image and its corresponding vessel mask. The biomarker extraction segment defines a function to calculate vessel density, tortuosity, fractal dimension, CRE, CRVE, and AVR from the binary vessel mask. Model training involves assigning risk scores based on biomarker values, specifically checking conditions for AVR, tortuosity, and vessel density to accumulate a risk score. Risk scoring continues for fractal dimension and branch points. Finally, the cumulative score is mapped to categorize the heart attack risk level as low, medium, or high. The model prediction segment includes loading functions for fundus images and masks, and initial steps for biomarker extraction, which will feed the trained model. The {predict _risk and _explain function completes biomarker extraction, uses the trained classifier to predict the risk level and class probabilities, and computes SHAP values for interpretability. SHAP explanation object is constructed using base values, SHAP values, and features. The SHAP forest plot is then generated to visualize how individual features influence the final prediction. SHAP explainability code segments show how to initialize the tree explainer on the trained random forest model and extract SHAP values and base values for a specific class of interest, such as medium risk. This code snippet demonstrates building the SHAP explanation object for a single sample and generating the SHAP force plot to visually interpret the prediction for that individual case. This is a placeholder slide for displaying the system output. The sample output confirms the system's functionality, from input validation to biomarker extraction, prediction, and SHAP explanation. For this sample, the system predicted low risk with high confidence. The SHAP plot visually clarifies feature contributions to the prediction. These slides detail the test cases used to validate the system's performance. In conclusion, our system offers a non-invasive, fast, and transparent method for early heart attack risk screening using retinal biomarkers and AI. The integration of SHAP makes the system reliable and clinically interpretable. Future work includes multi-class risk prediction, using deep learning for vessel segmentation, integrating multimodal health data, and developing a web or mobile application for greater accessibility. The references include book sources on image processing and machine learning, along with the project's GitHub repository and a video demo link. This slide is for addressing questions regarding